Everybody, this is where we left off on our review. And so the next question says, draw the Lewis structures for carbon monoxide, carbon dioxide, and the carbonate ion. So we have carbon monoxide, carbon dioxide, and the carbonate ion. And yes, I'm still having troubles, as you can see. Let me go ahead and grab this and pull it way over here so it is out of the way. Okay, so the first thing I want to do is be able to draw myself some carbon monoxide, CO, and then some carbon dioxide, CO2, and the carbonate ion, CO3 2 minus. So I'm going to have 4 valence electrons from carbon plus 6 valence electrons from oxygen, so 10 total, and this comes out to something that looks like that. Okay, and then for CO2, I have 4 plus 2 times 6, so that's 16 total valence electrons. That way carbon will be in the center, and I will have a double bonded oxygen on either side. And then for the carbonate ion, I have 4 plus 3 times 6 plus 2 more. So I'm going to end up with 18, 20, 24 electrons. So I'm going to end up with a carbon in the center and 3 oxygens bonded around it. And one of the oxygens is going to make a resonating double bond like that. And then when I get completed, of course, I need to show that in parentheses and write the 2 minus charge on the outside. And that will earn me all 3 points. Then for the next question, it says identify the species with the largest carbon to oxygen bond and explain your answer. You would have to say that it is the carbonate ion because it has a due to its resonating structure, it has a 1 1/3 bond, which is longer than a double bond, okay, but not as strong. So longer than a double bond. And by definition also, and a triple bond as well. Okay, so you have to be able to recognize that situation going on as well. Okay, so here we go. All right, so next, predict the molecular shapes for the 3 species. Explain how you arrived at your predictions. Okay, so predicting the molecular shapes for this one, and this one. Okay, so we end up with, we would say that each of the carbon monoxide and carbon dioxide would both be linear, but the carbonate ion would be trigonal planar. Both CO and CO2 are sp. No, that's not the best way to talk about it. Both CO and CO2 have 1 bonded pair and 2 bonded pairs of electrons around it. And there is no central atom on the carbon monoxide, but the CO3 has 3 bonded pairs and no lone pairs. So that gives us the trigonal planar. You could also say that it follows the AB3 format, whereas CO and CO2 simply follow an AB or an AB2 format, thus making linear. You could attack it either way. Okay, going on to our next part, we have in the reaction below, carbon monoxide is used to produce methanol. Calculates the C-to-8 bond energy given with the bond energy data. So we're going to be using the fact that this the heat of the reaction is given to us, and so we're going to follow the heat of the reaction is equal to this is all bond energy, so we're going to have reactants minus products. So I'm going to have negative 128 is equal to the heat of the reactants, which I have to recognize that this has a C to O triple bond, and this has H to H bonds like this, and this has C to H bonds and then an OH here like this. So that's what we're looking at right there. So I have the overall is equal to negative 128. And then for my reactants, I have C to O triple bond, which will be 1072, plus 2 times H to H single bond, so there's 436. And from that, I'm going to subtract 3 C to H bonds, which we do not know. It is not given to us. That's what we're looking for, plus 1 O to H bond, which is 463. And I'm going to pause it right there and continue my calculation. Okay, so this answer then, by my calculations, comes out to negative 536 kilojoules when we calculate that all out. And that is, actually that should come out to positive because this ends up being a negative on this side. So I should get 536 kilojoules. Okay, next question. Explain each of the following in terms of atomic and molecular structures and or intermolecular forces. So solid potassium conducts an electric current, whereas solid KNO3 does not. Solid potassium, K has a sea of mobile electrons due to metallic bonding. But KNO3 has electrons trapped in the crystal lattice. In other words, they can't move around. They are immobile. All right, and so they cannot conduct electricity. Okay, we're going on to the next one then. SbCl3 has a measurable dipole moment, whereas SbCl5 does not. Easy enough to do on that one. You can make the assumption that what you actually have is something like this with a lone pair here with those electrons, for those atoms there, whereas SbCl5 looks a lot like this with 3 things attached around. So you end up with SbCl3 has lone pairs, has a lone pair of electrons, but all dipoles cancel out in SbCl5. Okay. Normal boiling point of CCl4 is 77 degrees, whereas that of CBr4 is 190. This is due to, and you might be tempted to say, well, it must be due to hydrogen bonding, but it's not due to hydrogen bonding because there's no hydrogen bonding here. Instead, this is due to greater London dispersion forces, LDF, caused by higher relative molar mass. Okay. The next question, NaI is very soluble in water, whereas I2 has the solubility of only 0.03 grams per 100 grams of water. NaI is ionically bonded, whereas I2 is covalent, and in particular, non-polar covalent, making it very unlikely to dissolve. Okay, we go on here. Xenon has a higher boiling point than neon has. Again, when you're talking about boiling points, you must be talking about one of the intermolecular forces. And since there's no hydrogen bonding and there would be no dipole moment because it's all made of its own element, then what you have is LDF forces are greater. And do you see those 2 points there? Well, that means that you have to say why. Due to higher relative molar mass, MR. Okay, so there is that one for the ending of these this particular review, and I'm going to switch over to the other. Okay, so we need to go ahead and balance something like this. So when I'm looking at this, I can already see using my my shortcut that this is going to be an odd number, so I'm going to need a 2 here. So ultimately that means I'm going to need 12 carbons, and I'm going to need a total of 28 hydrogens, and so I'm going to need a 14 here. And that means I'm going to need a total of 24 plus 14, or 36 electrons, and so I'm going to need 18. I think, yeah, that gives me 18. What is the coefficient for oxygen? And I'm looking at that going, how did I do that right? 24 plus, so that's 36. That should be 18. And I'm not seeing a correct answer. Why is that? Did I balance it wrong? Okay, I have figured out what I did wrong in trying to do it too fast. I added 12 plus 14 and got 36. It should have been 24 plus 14, so 38. So this has to be a 19 here to get 38, and I'm still not seeing a correct answer listed here. I would love to hear from you as to what the correct balancing of this should be, because I don't think I see a correct answer here for this. Okay, so I'm going to move along because no reason to waste my time on this. Let's go on to which substances could be formed during the incomplete combustion of a hydrocarbon. Okay, so this is talking about incomplete combustion of a hydrocarbon. This is not talking about partial combustion of a hydrocarbon. Partial combustion of a hydrocarbon would make some carbon. We would never have some hydrogen made. We would never have some hydrogen, and partial and incomplete combustion would also make some carbon dioxide. So my guess is that by incomplete combustion, this question probably also meant partial combustion as well. So which substances could be formed? Could be formed. The reason why hydrogen can't be formed is it's highly explosive, and it would go ahead and combust, which would be making water, which would be one of the other things that it can make. So I think that our correct answer here came out to 1 and 3 only. So C was our correct answer. All right, we're going to move this along. Which statement about neighboring members of all homologous series is correct? Do they have the same empirical formula? Yes. Do they differ by a CH2 group? Yes. Neighboring members of all homologous series. Do they possess different functional groups? No, they do not possess different functional groups. Do they differ in their degree of unsaturation? No, that would mean that they're going to have different multiple bonds. So no, that's right. So we have to figure out between these two which statement about neighboring members of all homologous series is correct. And so it's using that terminology, all homologous series, and neighboring members. So I would be guessing, if I were to guess, is usually homologous series differs by the addition of a CH2 group, and I'm going to guess that this is our better answer than they have the same empirical formula. Because they use this terminology all, I'm betting that all of them do not actually have the same empirical formula. Okay, so there's that. But it does look to me like I would say, that looks like it has 2 correct answers. We're having a lovely time here, aren't we? Okay, so we go on to number 4. What is the IUPAC name for CH3, CH2, CH with CH3, CH3 on the end here? So what I have is some CH3 bonded to some CH2, and then a CH, which is bonded to a CH3 like this, and a CH3 like this. And so our longest carbon chain, we could say, is this is our longest carbon chain with that methyl group on the second carbon. So we would have a 2-methylbutane with a 4-carbon chain. So B would be our correct answer. And then which compound has the empirical formula with the greatest mass? So this one, you have to reduce all of them to their empirical formula. So I end up with CH3, and then I have C2H5, and then I have CH2, and then I have CH, and the greatest mass is going to be the one with the most carbons and hydrogen. So B was our correct answer there. Okay. So then we go on to number 6. Which compound is a member of the same homologous series as 1-chloropropane? It cannot be chloropropene. Close this. There we go. It cannot be chloropropene because that would change its saturation. So no. A 1-chlorobutane just differs by a CH2 group, so that's our correct answer. 1-bromopropane changes the functional group, so no. 1,1-dichloropropane increases the number of functional groups, so that won't work. So correct answer is 1-chlorobutane. And then number 7, which formula is a correct representation of pentane? That means we're going to have C5H12 as the empirical formula. So we have to be able to find the one that has C5H12. So this has 1, 2, 3, 4, 5 carbons, and that's correct, but it has 3 plus 2 is 5, 3 plus 2 is 5, 6, 7, 8, 9, 10, 11. So this one does not work because this is C5H11. This one has 1, 2, 3, 4, 5 carbons, correct, but it has 3 plus 3 is 6, 2 plus 2 is 4, so I have 10, and then I have 3, so I have C5H13, and that won't work. And then I have C1, 2, 3, 4, 5, so C5 is correct here, but I have 3 plus 6 plus 3. So I have a total of C5H12. Hey, that's looking good. And then the last one I have 1, 2, 3, 4, 5. So I still have C5, but I have H3 plus 9 gives me 12, 13, 14, 15. So that's also not working. So our correct answer would be pentane. Now you might be wondering, how did I know this? I followed the format of CnH2n plus 2 for an alkane. Remember, for an alkene, that's CnH2n for an alkene. All right, there we go. Continuing on. Number 8, which statement is correct about the reaction between methane and chlorine? Okay, so remember, that's where we have to have a free radical substitution going on. So it involves heterolytic fission and Cl1 minus ions. No, it does not involve Cl1 minus ions. It does not. And it actually involves homolytic fission, because if you remember, the Cl to Cl bond breaks apart and you end up with 2 Cl radicals. So you end up with an equal bond breaking. So heterolytic fission is going to be out, and you do not end up with Cl1 minus ions. You end up with Cl radicals. So that is our correct answer there. All right. Which formula is that of a secondary halogen or alkane? Okay, so secondary meaning that the halogen is attached to a carbon that is attached to 2 other alkanes. So halogen on the carbon attached to 2 other carbons. Okay, so we need to take a look here. This one is a carbon attached to 1 other carbon, so that's primary. This one is a carbon, that's our secondary, a carbon attached to 2 other carbons. It's attached to that carbon and it's attached to that carbon. Here, this one is simply a primary, a carbon attached to 1 other carbon right there. And here, this one is tertiary. This is a carbon attached to 3 other carbons. So our correct answer should have been B there. Okay. And then we go on to this question here. All right, so what possible termination products could be formed in the monobromination of ethane? Okay, so that means single bromine is being added to ethane. Would we have a chlorine radical? No, we would not have a chlorine radical. Would we be able to make a butane? Butane would be made of CH3CH2 plus a CH3CH2. Yeah, that would work. So double I is correct. Chloroethane. This looks like I changed the question but didn't change the answers. So this would have been a bromine radical. And that would be wrong anyway, because in a termination, you're not going to have the radicals formed. So that means we get to also get rid of an ethyl radical as well. Might we make a chloro or chlorine molecule, yeah, we might make a chlorine molecule, so that's okay. And, or that would be a bromine molecule, yeah. And then might we make a bromoethane, yes. So 2, 3, and 4 should have been our correct answer, and B was our correct answer there. And that was because I played with the question when I made this test. Okay, last question on this particular part. The structural formula for CH3CH2 parentheses 2, CH2 CH3. Oh my goodness gracious. Okay, so I have CH3CH2 bonded to a C, and that is also bonded to a CH. So let me get this right. CH3CH2 like that, and that has an H on it, but it is also bonded to another CH2, and then it's bonded to a CH, but that CH is bonded to two CH3s, so it looks like this. Woo! That was exciting. It does not look like we need to have any double bonds here. 1, 2, 3, 4. 1, 2, 3, 4. 1 here, 2, 3, 4. Yep, everything is accounted for. So that is what we have going on there. Oh, that's crazy talk right there. Good thing I didn't also ask you to name that thing. Let's take a look and see if the next question is, oh good, the next question does not ask us to name it, but let's go ahead and name it anyway. Let's assume that what we actually have is our longest carbon chain ends up being right here. So if that's our longest carbon chain, it is 1, 2, 3, 4, 5, 6 carbons long. So this is going to be a hexane, and it is it has a methyl group on the 5th carbon, and it has an ethyl group on the 3rd carbon. So this would be 3 ethyl dash 5 methyl hexane, just for good measure. Now we know. Okay, yay. Let's go ahead and move on to the next question. Identify the functional group present in CHO or HCO, CH2, CH3. So when you draw this one out, you end up with C with an H here and a double bonded O here, and that's going to be a CH2 and a CH3, just like that. How did I know that has to be the case? Because I can see that I have to have a correct number of things bonded around my carbons. And if I just do an H on one side and an O on the other side, even if I double bond the O to the C on one side and the single bond to the O on the other side, I won't be using the right number of electrons. So if that's the case, when I have the double bonded O and the H on the ending carbon, I end up with an aldehyde. That one is an aldehyde. Which of the following molecules contain the same functional group? We are looking for functional groups. I am seeing an OH here, and an OH here, and an OH here, but I am not seeing an OH here. That one is an ether instead. Those three, number 1, number 3, and number 4, are all alcohols. They're all alcohols. Okay, so that would be our correct answer for that one. All right, so let's go on. Look, it's even labeled for you, 1, 3, and 4. Okay, so we're going to name the following compounds for this. So let's go ahead and see if we can figure these out. This one, I've got a CH3. Nope, not what I wanted to do. Let's get rid of that. Here we go. And so this one, I have a CH3, CH2, CH2 carbon, and then I have this thing attached to it, and it's going off on 2 sides, and then I have, okay, so this one I'm going to have to draw out, because if I don't, okay, so let me just add to what I have. What I have is the CH2, CH3 going this way, and I have this CH2, CH3 going this way. That's what these two things are. So I get to erase those because that's where they are. And so I just have to figure out how to name this. And it turns out that it doesn't matter which way I go. I'm going to end up with the same number of carbons, whether I have 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. So it's all going to be heptane. and then I just have to figure out, well, what is attached to the heptane. At carbon number 4, I have 2 propyl groups, so 4, 4 dash dipropyl heptane. Okay, so for my next one, I have the same thing happening again. I'm going to have a CH3 group coming off of that carbon and one here, and so I'm going to have 2, 2 dash dimethyl. And my longest carbon chain is right down the middle here. So 1, 2, 3, 4, 5, dimethylpentane. Okay. And this one is going to look like 1, 2, 3, 4, 5. So that's a pentane. And it looks like I have 2, 2, 4, 2, 2, 4 dash trimethyl pentane on that one. This one is going to be ethyl cyclopentane, and I'm not going to have to number that because it will be assumed that the ethyl group is on the first carbon. This one is 1, 2, 3, 4, 5, 6, 7. This is plain old heptane. This one here, it looks like we're missing number 4, but I bet it's down below. This one here is going to be 1, 2, 3, 4, 5. So that one looks like I have 3 dash ethyl pentane. And then this last one, it looks like I have 3 dash chloropentane. All right, so let's go ahead and continue downward. Write the abbreviated structural formulas and name all the structural isomers of pentane molecule. Okay, so let me see. I believe that means I'm going to have 3 of them. The first one is 1, 2, 3, 4, 5. That's going to be pentane. And then I'm going to have 1, 2, 3, 4. And then I can have a methyl group attached like that, and I'm only going to do that so I can see it, and so that's going to be 2 methyl, can't spell, methyl butane, and then I'm going to be able to do, okay, I can do 1, 2, 3, and then I can do a methyl group off each side, so I can have 2, 2 dash dimethyl propane. And I think that covers it. All right. I think there's 3 of them. And I think I've covered all of that. Okay. So there we go there. And alkanes are important starting materials for a variety of products. Didn't explain the trend of boiling points for the first 5 members of the alkane homologous series. As the number of carbons increases, the boiling point increases due to greater relative molar mass and polarizable electrons. That pretty much covers it there. Okay. You could also say greater London dispersion forces. That could be added as well. Okay. There we go. All right. Describe 2 features of a homologous series. The 2 most common features are increases by the addition of a CH2 group and gradually changing physical and chemical properties. Physical properties. Much like the boiling point is increasing. Okay. State the products of the complete combustion of alkanes. Complete combustion leads to carbon dioxide and water. That would be it right there. Okay. All right. explain using equations the following steps in the free radical reaction of methane with chlorine. Okay, so our first step, our initiation step has to be the breaking of the chlorine bond. So this is going to be a Okay, so explain using equations the following steps in the free radical mechanism of the reaction of methane with chlorine. So what we have to be able to do is we have to be able to break the chlorine apart using UV radiation, and what we're going to make is two chlorine radicals. And so that's our initiation step. And then our propagation step is pretty much any step that involves the creation of another radical. So then we're going to have a chlorine radical that can now attack the methane. And so we have some methane here with CH4. So we're going to have 4 H's all the way around it. And so we're going to end up with making HCl because we're going to break the H off. So these two are going to get together, and then what we're going to be left with is a CH3 radical. Okay, so that's our propagation step. And then our termination step can be any combination of two radicals. So we could say that our methane or our methyl radical and another chlorine radical could get together, and we could come out with methyl chloride, or naming it the other way, chloromethane. All right, and I think for everybody that ends up being the end of this particular test. Yep, it is. Okay, now since it does have 4 marks, you might wonder where are the 4 marks of that last one. And the 4 marks of that last one ends up being in the initiation. You're going to have the creation of the 2 chlorine radicals, but you have to have the UV in there as well. Okay, I'm going to pause this and we're going to go to the very last example. Okay, so this is an alkenes test from several years ago. It says which statement is correct? Oxidation involves loss of electrons. As you can see, we were probably reviewing some oxidation and reduction as a part of the of this particular unit. And so we might as well go ahead and answer these. And to remember this, you need to simply remember that Leo, the lion, goes grr. So loss of electrons is oxidation, gain of electrons is reduction. And so which statement is correct? Oxidation involves loss of electrons. Yes, that's true. It does not involve a decrease. It would actually be an increase in oxidation state. So oxidation involves a gain of electrons. No, that is false. Reduction involves a loss of electrons. No, that involves a gain. So no. So reduction involves a gain in electrons and a decrease in oxidation state. There is our correct answer for that one. Next question. Percentage by mass of the elements in a compound is given there. What is the mole ratio of C to H in the empirical formula of this compound? So let's do a little bit of this. We have a carbon that is 72. Let's make sure that we can write on our page. We've got 72 grams of carbon, 12 grams of hydrogen, and 16 grams of oxygen. So dividing each by their molar masses gives us, whoops, there we go, 1, and divide that by 12. There we go. And that's going to give us 6. And then we're going to divide by the smallest one, which ends up being dividing by 1. So we end up with C6H12. That doesn't look right. Oh. Okay, and we want to know the mole ratio between C6H12. So that ends up being a 1-to-2 ratio. So correct answer here should have been B. Okay. So let's continue onward now. What product results for the reaction of CH2 double bonded to CH2 with a Br2? And so you're not going to lose any hydrogens, but you needed to make sure that your BRs both end up on here. So D was your correct answer here, because you're going to break this double bond here, and you're going to end up with 1 space each for the BR to attach itself, just like that. Okay, next one. Give the IUPAC name of the following compounds. Okay, so on this one, we have to be able to say what is going on here. So on this one, I have a methyl group on the second carbon, and I have a double bond starting on the first carbon, and then I have an extra methyl group on that last carbon, and we're going to number from the side closest to the double bond. So our carbon is 1, 2, 3, 4, 5, 6 with a CH3 coming off the side, the CH3 there. So I have 2, 6 dash dimethyl, and then I can say 1 dash hexene, or I can say 2, 6 dash dimethyl hexene, and that would be okay. On this one, my longest carbon chain would be right here. There's my longest carbon chain, and then I have an ethyl group coming off of the second carbon. So I have 2 ethyl, and I would get to call that 1, 2, 3, 4 butene. And I wouldn't have to call it 1-butene. As I said before, you could just call it butene, and the assumption would be made there. Okay. Going on, number 5, draw the structure for each of the compounds named below. Okay, so I have 4-methyl, 2-pentene. Okay, so I have CH3. Let's make sure I can write on my paper. There we go. I have CH3, CH, double bond to CH. That's where the double bond is on the second carbon. Then I'm going to have a CH2. Actually, I won't have a CH2 because there is a methyl group coming off of that right there. And then I have a CH3. So that is that one. And then I have a cis-1 bromo 2-pentene. Okay, so this is a pentene. So there's 1, 2, 3, 4, 5 carbons. And the double bond is in between carbon number 2 and number 3. So there's my double bond. And I'm going to need to be able to show it as a cis. So I need to be able to make sure that I draw this correctly. So let's make sure that I'm going to show it correctly. So here I'm going to have a CH3 here and H here. And then on the other side, whoops, on the other side, cis-1 bromo, okay, cis-1 bromo 2-pentene, okay, 2-pentene. 1, 2, 3, 4, and let me make sure that I do this correctly. This disappears. Okay. So this CH2Br, there's the 1 bromo attached there. 1, 2, 3, there's an H there, and there's an H there. I think that takes care of everything for that one. This is 2 bromo 1,3-butadiene. Okay, so 1,3-butadiene means that I have a double bond between the carbon number 1 and carbon number 2, and then I have a double bond between carbon number 3 and carbon number 4, like that. So that's my butadiene, and then I've got 2 bromo. So I've got a bromo here, and that takes care of all 4 there. So that means this has to have 2 hydrogens coming off of it, and this needs a hydrogen coming off of it, and this is going to have 2 hydrogens over here like that. That was exciting. Okay, which of the following molecules is most likely to undergo an addition polymerization reaction? That means that we are looking for an alkene. The only things that can undergo an addition polymerization reaction is an alkene. And then predict the repeating unit. So I'm looking here and I'm looking for an alkene, and I'm not seeing an alkene on this. My giveaway on the alkene is going to be a CH. In other words, there is a double bond here. And so there it is. There's my double bond. It's not going to be here. That is the carboxylic acid, and that is not going to be the kind of double bond. We're looking for this double bond right here. Okay, so if that double bond breaks, then what we end up with is CH with a bond out this way, bonded to a CH2 with a bond out this way. CH has a CH3 attached. So then we're going to be able to say that is the repeating unit. And what I broke was this bond here, and I moved the extra bond to here, and the extra bond to here, and this I just transferred down to here. Okay. All right, number 7. Which step in a multi-step reaction is the rate determining step? It is always, as we discussed, it is always the slow step. So it's not necessarily the first or the last. It's not the step with the lowest activation energy, because that would be fast. It would be the step with the highest activation energy, because that requires the most time to build up that activation energy. Okay. Number 8, the rate of a reaction between two gases increases when the temperature is increased and a catalyst is added. Which statements are both correct for the effect of these changes on the reaction? Remember, adding a catalyst simply increases or changes the pathway of the reaction and decreases the activation energy. So anything that either says activation energy does not change or says activation energy increases gets to go away. And then collision frequency was not activation energy. So that leaves us these two. Increasing the temperature does not change the activation energy. So saying that the activation energy does not change is the correct thing. So C was our correct answer here. Okay. And then completely answer the following questions. Write the structural formulas for the products of the following addition reactions. So ethene and bromine. So we should have ethene and bromine means we're going to end up with CH2 with a Br here and a CH2 with a Br here. And then this addition ends up giving us a CH2 with an extra H added here. And then we're going to add a CH, and that's going to be the one that the chlorine goes on by Markovnikov's rule, and then we end up with CH3 on the end like that. Okay, on this one we're going to be adding the O and the H to it, so we're going to end up with a CH3 followed by a CH. The OH is going to go here, and the CH2 is going to have that extra H added onto it, so you could have written that as CH3. Okay. Equation based on the following reaction scheme is given here. Okay, so there it is. Give the structure of the geometrical isomer of W. Give the structure of the geometrical isomer. So if this was both on the same side, then we want the structure to show them on different sides. So we would show this C's double bonded in the center, and the CH3 here, H still here, but we would move that H to the top. We would have the CH2 and the CH3 like that. State the full name of W. So we would call that cis. Yes, hold on just a minute. Okay, so we're trying to give the full name of this one. So this is going to be cis-2-butene. Cis-2-butene should have been our correct answer on that one. Okay. Going on, then it says what type of carbocation is most stable and is most commonly is the most commonly found at X and Y. Okay, so it's referring to X and Y there as most commonly found, and so the most stable carbocation you should be identifying that as the tertiary carbocation. Write equations using curly arrows to represent the movement of electron pairs to show the mechanism of the reaction in which X is formed. Okay, so that means we're adding bromine to the double bond. And so let's go back and make sure the double bond was on the second carbon of the butene. Okay, so we have CH3, CH to CH like that. And then we had a CH3 on the end, and we are adding one bromine to it. So that means we're breaking the HBr bond. Okay, so what we have happening is the arrows pointing to the bromine, going back to the bromine, and so what we have now is a hydrogen being attracted to those pi bonded electrons. So the hydrogen is going to break those pi bonded electrons, and what we're going to end up with is a CH3 CH2 because the hydrogen jumped on, and we're going to have a CH here with a carbocation right there, and it has the CH3 on the end. And what it's going to add to it is the Br that is now negatively charged, and it's looking for a place to bond. And so this will bond by bonding right there with that. So actually, yeah, just like that, because this is actually positive. This is incorrectly drawn. That should not be a radical. That should be showing as a carbocation like that. So it's got a place for the Br to go on. And so that's what you end up with there. Okay. So Markovnikov's rule is sometimes useful in predicting the major product in this type of reaction. Explain why this rule cannot be used to predict, and that is simply because you have one of your reactants is symmetrical. And then what reagents and conditions are required for the conversion shown below. So the conditions that you're going to need are, in this case, are some hydrogen gas and a catalyst of either nickel or platinum. That were the two things that you needed. And what test could you carry out on both the starting material and the product to show that this reaction had occurred? Add bromine water to see if there is a color change. If there is a color change, then you know that you have not had the reaction take place. If there is not a color change, then you know that the reaction has taken place. Okay. Okay, so in this problem, we haven't really talked about what a enthalpy level diagram looks like for the two-step problem, but that simply means that it's going to have two activation energies. So we would have the energy on one side and then the reaction coordinate on the other side. So we're going to start with some reactants. And then it says our first step is the rate determining step. That must be the one with the highest activation energy. So it's going to look like this. And then it says that it's endothermic. So that means the products have to end up higher than the reactants. So they're ever so slightly higher there. These two humps indicate two different activation energies. Endothermic is taken care of by the fact that delta H of P minus R comes out to a positive number. So there's that for the delta H labeling. Oh, activation energies. Here is the rate determining step, activation energy, and here is the faster step, the second step for the activation energy there. Okay, you are not going to have one like this on your test, so not to worry on that. All right, so then we go on to, I think that might have been the ending, and it was the ending. Okay, everybody, thank you very much.